The initial title of this paper was, as the chairman said, Confusion by Sparking Nitrogen Isotopes, Energy Balances and Stress for Byproducts. We finally decided to change it to a more ambitious and maybe provocative title, which is in fact strategy to prove the reality of cold fusion. Before starting this presentation, I would like to say that I'm not intending to go very deep in technical details of the work which has been done, because this has been extensively published in a 23 pages paper in the issue of September of Fusion Technology. So see if some of you would be interested in these details. I have a number of references in this paper. I'm not paid by the editor for his time. I think that to define this kind of strategy, we need to answer two questions. The first is, what are the conditions for fusion to be recognized as a reality by the scientific community? I think that is very important, because in the outside world, there is a number of experts in the various fields we are involved, that are involved in cold fusion, and it seems to us absolutely necessary that they are convinced that cold fusion exists. And the second question is, what kind of research project can meet these conditions? We think, in fact, that two main conditions are required. The first is to try to eliminate artifacts from experimental data and propose a plausible theory and check that the data fits the theory. I'm not saying that you are all playing with artifacts, that's obvious, but what I'm saying is that this is a very difficult and, I would say, sensitive subject on which you can, in fact, do, even if you are very careful, many artifacts. And the second condition is to involve critical but open-minded scientists, which are experts in the various fields playing a role in cold fusion. And it's maybe not very difficult, not very easy to find this type of people. Just to show you that I'm not coming here after 4 years to say, hey guys, this is the solution. I just want to show you what I did personally in this field. I started in May 89, just after the application of Freshman Ponds, by a proposition to carry out excess heat release in metals. In fact, by using a spark in the hydrogen between metallic electrodes, we find Shell, which is a company active in the field of energy and for which I'm working for, filed a patent in July 89 on this idea. I worked between May 89 and September 92 on this concept within Shell, and published the work done in September 93. And at a certain point in time, we agreed that it was necessary to have an exposure to the outside world of this work, because scientific committee are looking on what I'm doing, and of course are very critical on what I'm doing, but they accept a number of ideas if I can prove it. So that's the reason why Professor Foss and Professor Nero are here, and I've co-signed the paper. The work is still financed by Shell because we want to have an idea, a final idea of the value of what has been done. So after a certain amount of discussion, we arrive at this following strategy. First, I think we have to have a reproducible, long duration on steady-state situation. When I say long duration steady-state situation, it's several weeks. Excess power generation of sufficient size, and we are aiming at tens of watts. For a number of reasons which we can evidence afterwards. The second condition, I think, is to propose a kind of, I would say, hypothetical but possible nuclear reaction scheme. You probably have noticed, as I did, that there are a number of byproducts which are proposed by various experimenters, and I think it's needed to have something behind, a kind of idea which can explain all that. And the third thing is to track the products of this nuclear reaction, of course taking into account possible artifacts and eliminating them. I think the next step, but this has to be the last one, will be to improve the theory on reliable experimental facts. So, the first step is to have a reproducible, long-duration excess power generator. Before explaining what we are going to do, I just want to give a number of indications of the approach I have been following. The idea was to spark in hydrogen isotopes at atmospheric pressure between two electrodes, two asymmetrical electrodes, one of them at least being made of palladium. The idea behind was that when the spark is hitting an electrode, well, two things happen. The first is you have a great amount of atomic hydrogen or deuterium generated, which can, of course, increase as the impact, the concentration of hydrogen or deuterium in the palladium. And the second characteristic of the sparks is that at their impact, the mean intensity is 1 or 2 amps. The impact section is between 10 minus 5 to 10 minus 6 square centimeter, which means that each time one spark impacts on palladium, you have an inlet of atomic hydrogen, and you have a high transient electrical field in the palladium. When I'm saying high, it's not high like in an accelerator of particles. High means 100 volts per centimeter, which is of course much too low to generate any acceleration of protons in the palladium to overcome the Coulomb barrier. The idea of that is only, I would say, to increase the interaction between proton, electrons, and all what is in the metal. And if you look at what can happen using electricity in gaseous hydrogen isotope, you see that sparks can do that. Ozonizer discharge also, and of course high current density pulses in hydrogen-loaded batteries. So that's the idea which were behind this energy patent, this patent energy source reactor with a volume of 300 cubic centimeters. This is a copper tube of 1 centimeter diameter connected to Earth. This is a foil of either palladium or any metal we want to test, which is put in the form of a cylinder around this electrode holder, and in front of it you have a second electrode, which is dissymmetrical. This is a point electrode, which is connected to a high voltage generator. So this is basically the reactor we are using. What is the situation for the time being, which is described in the paper I mentioned? We observe long duration power generation. When I'm saying long duration, is up to 1,000 hours, with 1 or 2 watts excess power generation. We are increasing it to 5 to 10 watts, and the results on the ozonometer type of discharge, which I'm going to present you, opens the road for an upscaling to 100 watts. We found that in September 92. Just to show you the exact meaning of these 2 watts excess generation we are obtaining, it's clear that I have used a rather complex calorimetric system, which is described in the article, using a car ignition system to generate high voltage through a coil, which is then feeding the reactor. So there are 1 mass flow calorimeter and 2 heat flow calorimeters. The powers are generated as between 10 and 15 watts in the ignition system, 6 to 8 watts in the coil, 3 to 7 watts in the reactor. So the excess power is the difference between this free heat release compared to the electrical input here, and it's typically 2 watts, which is basically some 10% of the overall heat release of the system, but which is nearly 100% of the intake of the reactor. So this is a point we have to keep in mind. In order to be in a position to upscale to higher powers, we made a number of experiments with ozonizer types of discharge. And for those who are familiar with this type of discharge, you can use either what is called glass metal ozonizer discharge, which is a discharge in which you have 1 dielectric barrier and 1 electrode in contact with the discharge. And the second type of discharge you can use is the so-called glass discharge ozonizer, in which the metallic electrodes, none of the metallic electrodes are in contact with the gas. You can see it here in this scheme. This is the actual reactor I'm using, and this is the 1 dielectric barrier type of discharge. So you see that you have 1 metal electrode, and a dielectric here, and the 2 dielectric barrier ozonizer discharge. You have the 2 metallic electrodes and 2 dielectric barriers. Doing that, you can compare very comparable situation where the only difference is that 1 discharge does not see any metal, and the other sees the metal in that case, palladium. The results, which I'm going to show you, clearly shows an excess heat production in the case of the glass metal discharge, and no excess in the glass discharge. So the contact with the metal is needed to have an excess energy. Well, these are typical results on experiments which are done, as all the experiments I've done, on a steady-state basis. That is, the system needs roughly 2 days to stabilize, and then measurements are done, and experiments are typically on 3 days. That is, the excess power here is observed for 3 days, and as I told you, lasts for several weeks. With one barrier, you see that this is the power to the reactor. This is the excess power observed. So you see that the mean value of the electrical energy to the reactor is 3.11, and this is the excess power. With these standard deviation here, shows that this is a situation which is statistically different from the situation of a double wire oscillator, where you have a power input of 2.7 and an excess power of 4.07 with a certain spread of the value with a standard deviation of 0.57. So it seems clear that under absolutely comparable conditions of discharge, if there is no metal in contact with the gas, there is no excess energy. And the second point, interesting, is that it's rather easy to upscale and also measure the power of discharge with no emission of 1.2. The second thing I said is that was needed in the strategy was to propose an hypothetical reaction scheme and to check how that would be verified by experimental data. In the paper of fusion technology, I proposed a scheme based on three-body reaction involving one electron, one hydrogen isotope, a second hydrogen isotope, or a metal nucleus. This reaction proceeding through a virtual neutron state or polyneutron state, which of course involves only the weak electronic force in high electron, proton, and nuclear concentration, all of these having low thermal energy. If you accept, which I'll discuss a bit more in detail, if you accept this hypothesis, then successive reaction can take place, and this succession of reaction can give a very varied pattern of products depending on the exact experimental condition you are using. Another characteristic of this approach is that part of the fusion energy is lost with the neutrinos involved in the system. And the last point is that some daughter nuclei of this reaction can be unstable and have beta or X-ray emission, which can contribute either to the emission of you observe, or of radiation you observe, or to the heat release. Of course, I'm aware that you have a number of theoretical problems with that. Well, this is exactly the schema in mind. If you take the three-body system, proton, plus electron, and the end product, the material, neutrino, you cannot go from 1 to 2 because of the wire. You cannot go from 1 to 3 because the P plus N plus neutrino is in fact forbidden by laws of energy conservation. What I call virtual state is the passage from 1 to 2 through 3, which you cannot see. But I don't know, I know of course about the cross-section, which is a great problem. What we have done, in fact, is just accepted that hypothesis, which you can play with, of course, by making neutrons from deuterium, etc., and just accepting that this hypothesis, which is still an hypothesis, we have drawn all the will show you some examples. In the case of electron and 2-hydrogen isotope, which leads to the conclusion that the heat release from hydrogen and deuterium are comparable, that the final product is probably helium-4, maybe lithium, that you have a possible small neutron emission. I will have a look at the electron plus hydrogen isotope plus metal in the case of potassium and in the case of palladium. So, if you look at the proton chain, the first reaction I'm invoking, this one, which is of course a reaction which is in the standard solar model with a very low cross section. 2 hydrogen plus 1 electron gives deuterium plus a neutron. The second one, which I have in mind, which does not happen in the sun, because probably afterwards the reaction in the solar model, you have a reaction implying the strong nuclear force which is much faster, so they cannot happen in the sun, but there is no reason if you accept this one for this one not to happen. So this one is hydrogen plus deuterium plus E minus giving tritium plus a neutron. Of course the tritium is radioactive and will decay into helium-3 by beta emission. Then you can have either proton plus tritium plus electron giving an hypothetical hydrogen-4, I will comment on that later. You can also have deuterium plus deuterium giving this hypothetical hydrogen-4, and you can have even, I'm not saying that's true, but you can envisage to have deuterium plus tritium plus electron giving an hypothetical hydrogen-5 plus a neutron. And then you have to look at what happens with the products of these first reactions. Tritium, of course, will give helium-3, as I said. If you accept the idea that it is a chain, successive reaction, of course, the amount of the intermediate products are very dependent on the relative cross sections, and you can very well imagine that helium-3 can be found in a very low amount because it's only a step in the reaction. Now we have arrived to a second difficult point, which is the case of these 4 hydrogen. 4 hydrogen have been more or less observed experimentally with a lifetime of 10 to the minus 17 seconds, so it's very unstable. Hydrogen-5, there is no experimental data. The beta decay of hydrogen-4 could explain, in fact, the helium production, but of course there is a problem here, is what is left in the reactor for, you have 20 made roughly available in reaction 3 plus 7, or 3 plus 7. What is the repartition between the neutrinos, the betas, and the recoil? I have no answer for that. If you look at the production of hydrogen-5, this is an typical hydrogen-5, we are in the same situation as this one. If you accept that, of course, it will beta decay to helium-5, then you have the possibility of rationalizing production of neutrons by the further decay of helium-5 to helium-4 plus neutron. But there are problems to understand exactly the detail of the reaction. If you try to make an evaluation of the energy left in the reactor, you arrive to the conclusion that if you are in a situation where the reaction, successive reaction starting from hydrogen can be fast enough, then you have the same, more or less the same heat release started either by hydrogen or deuterium. Sorry, I'm going on. You can envisage also lithium production virtual neutron state, G-neutron. The reaction with a proton is endothermal, but the reaction with a deuterium is exothermal and can lead to production of lithium. If you look to things like potassium, then you can have this type of reaction, either a virtual neutron or G-neutron or G-neutron, reacting with these various isotopes of the potassium through this virtual state, and giving this isotope of potassium, which then can decay or beta decay to calcium 42. The case of palladium, I just want to mention it very quickly. You can make the same calculation, but of course they are a bit more complicated. I don't want to go more in detail. They are in the paper which I've prepared. But you can see that you can have a number of products which can be either stable or can undergo beta decays and explain a number of observations in various experiments. So this is only an hypothesis. And what we are aiming at is, as there is a great number of, in this hypothesis, a great number of possible byproducts, we think it's absolutely necessary to have a high excess power generation. That's why we are aiming at tens of watts on several weeks. And we are planning to first start with the simplest system, which is hydrogen palladium. We are planning to have information on tritium and helium formation by quantum melting, and we are contacting the best experts in France to carry out these analyses, of course checking artifacts. You will see in all the slides, check artifacts, etc. Neutron measurement, we are planning to use a method which was used in the previous work, which is track exchange, because this is not sensitive to big electrical pickups, because when you are using plasma, whatever the pressure you always have, the mass between from the electronics. Probably we can use a VHS counter with the ozonizer or pulse currents, because there is less electrical pickup with this discharge. And if there is an indication by this method, which I'm not going to develop, it's explained in the paper, byproducts in activated electrodes, meaning either isotope of palladium or silver or things like that, only if they seem to be in great quantity by SIMS or microprobe, because this also are very difficult to detect. So, this is what we have in mind, and we are for the time being increasing the power to 10 watts by modifying the present reactor, and we are ending the design of a 50 to 100 watts reactor based on the amount of discharge in order to be able to make this byproduct track. So my conclusion would be that, well, there are a number of intriguing things in the field of fusion. We have measured in shell an excess energy production, which seems to be reliable and reproducible. We have the idea that the byproducts may be numerous, that we are going to check all that with the most critical approach in order to say at the end there is nothing to it. But of course my personal wish is that the final conclusion will be that fusion is a reality. Thank you for that.
We have a couple of announcements after this talk, so we've be talking, and so the session changes. Do we have any questions?
For your theory, you're saying you're wanting. For your theory, you're saying you want to go to PPE cross-section working for the electron. Now, I've been working in stellar evolution for the last few years, and this is quite well known. It's about 10 orders of magnitude less than the proton-proton, which is very low. It's 10 to the minus 47 square centimeters. So the PPE exists, it's
experimental errors of your calorimeter, because from the data you presented, one can deduct you have a calorimeter with 10 millivolts accuracy. Can you please specify the errors and something like that?
If I understand well your question, what you are asking me is what the degree of confidence of the excess power.
What was the experimental error in defining excessive power?
We carried out roughly 100 experiments, and what I put in the paper, I don't know if you read it, but it's explained in detail, so I don't want to go now in detail there. All experiments which are called reference experiments or control experiments, which are experiments which were done with a different gas, sparking in either argon or nitrogen, or the experiments with double wire oscillator. All these experiments, there are 60 of them, have the standard deviation of 0.35 or 0.4, I don't have the exact figure in mind, watts, and an mean value of 0. Okay? If you look at the experiments on which we are expecting heat release, there are 40 of them, and the mean value is something like 2.1, and the standard deviation is 0.4, expressing watts. Okay?
So the second numbers after the point where it is just.
Sorry?
The second point after the 0 is meaningless. So is it true? So you gave numbers something like 2.47 watts. So 7 is just meaningless.
Yeah, okay, so it's an average value on the various experiments, of course. If you give a value, the mean value, and the standard deviation, you have no problem. Okay?
Next question.
How much the voltage is you apply to your reactor?
Sorry, what was that?
The high voltage, how much?
The spark generation in atmospheric pressure, hydrogen is very well known. You have, I applied a source of 15 kilovolts. 15, and the voltage during the spark, which I recorded with the oscillator, etc., I have all the data, is something like 2 kilovolts. When the spark has initiated, the potential difference between the electrode goes down to 2 kilovolts.
The frequency.
Sorry?
The frequency.
The frequency. The thing which was used was a car ignition system, and the natural frequency of the equipment was 2000 hertz, but it was trained on oscillation at 2000 amp oscillation at 2000 hertz every 300 hertz.
All right, thank you. I think we should discuss this later, and Al's got some things to tell us about, as well as Tom Hassel just before lunch.
Yes, for my 15 seconds of glory here. We're again running parallel sessions. Take your complaints like Cooper back, but understand that if we weren't running parallel sessions, we would get done just barely in time to start the next day. Nuclear parallel session 2 will be in this room, as you can see. Calorimeter number 2 will be in Regency C, and theory and parallel 2 will be in Regency B. These are posted outside also. I think Tom asked us a couple of times.
Thank you, Al. There are a couple of lost and found items that you can get if you lost something in the last few days. In one of the rooms, the lobby, the administration lobby for the hotel, they will have them lost and found there for you. I presume that everyone here who's bringing a friend or a spouse has a ticket for them at the luau tonight. And if you don't, see Linda after this. Finally, I'd like to announce with some degree of pride that the Office of Naval Research has made a significant financial contribution over and beyond the bringing of their personnel here. And so when you see Bob Nowak, would you thank him for that contribution from the Office of Naval Research? Thank you very much.
privilege of opening this session. And I'd first like to acknowledge the important contributions from colleagues here at the Fairleigh International team of people from, this pointer's not working. Oh, there, I have the wrong one. Dr. Bear Beckhoff from Pakistan is visiting us for a year, and we have a Fairleigh International team of other people involved in this research. Actually, if I had the opportunity, I'd rename the title of this talk instead of multi-layer thin film heat production. I would talk about a disintegrating electrode. So that's what we have developed as a self-destructing device, as I'll explain in a few minutes. The motivation behind this has to do with the theory which we've developed and presented in previous meetings called swimming electron layers. Namely, if one takes a set of thin films of alternating layers, such as this example, which would have alternating layers of palladium, titanium, and the electrolyte or other deuterium gas on this side. This theory is that if you select the thin films such that the Fermi level, energy levels in the alternate films are quite different, maximized, then the potential differences create a high density of electrons at the interface between the layers. And in this region, screening or whatever happens to enhance reactions would enhance reactors at the interface. Or put in a more simple fashion, this gives us multiple surfaces on the internal volume as opposed to the outer surface. In fact, if you have simply an outer surface, there's also a electron layer in it. More details of that theory are given in references 1 through 3 in the abstract. If you want to delve into that, we've gone into fairly detailed theoretical analysis in previous presentations. Today we talk about experiments that we've done with this technique. And first we have laid down, using electron beam vaporization techniques, thin films of the type I just showed, palladium, titanium, and so on, 100 angstroms thick each on both sides of a stainless steel substrate to provide strength. And we put on the outside a 60 angstrom film of chromium. The chromium was our attempt to provide a barrier to help sustain the deuterium density internally. The calorimetry for this type of measurement has been done using a fairly simple but reasonably accurate dual electric cell type of arrangement, where we have paired cells. We calibrate them with pure stainless steel electrodes of the type that I showed, and then substitute in one a multi-layered electrode. So the actual electrolytic cell is an open type of cell. We have minimized volume around the electrodes, one electrode being a platinum wire, the second electrode being the thin film type. We've minimized the volume to get a maximum sensitivity. We have a gas collection box here so we can observe any possible differences in gas evolution which might cause difficulties. Calibrations for this, today I showed two regimes, one a low temperature or low current regime, the other the high current, and the calibration for these paired cells are shown here. for two different cells, and we get a fairly nice linear calibration with the 0.2 amp current. The electrodes, as you remember, 2.5 centimeters square. Gas production also fairly linear. This is shown for two different power levels as a function of time up to 600 minutes. And a measurement of the temperature in the cell for two different power inputs, 0.5, 0.46 watts. And this continues with the low current type of operation. I'd like to superimpose on that the results that are shown with the thin film type of electrodes. The thin film electrodes, we've run 5 thus far. Incidentally, these are very tricky to make, so it usually takes us considerable time to make the electrode itself. And the colored dots are two different runs with these thin films contained. You'll note that there appears to be a slight deviation that occurs at longer times. And this deviation continues until the point where the foils disintegrate and fall off the surface. And this happens at different times depending somewhat upon the bonding, the goodness of the bonding it would achieve with foils. Now, while the temperature, excess temperature rise that appears to occur with the foils is orders of 1/10 of a watt or so. If you calculate the power density that corresponds to in the foils themselves is exceedingly high. With these thin forms of foils, it's something like a kilowatt per cubic centimeter. And so I guess the destruction is not unexpected because with that temperature and different coefficients of expansion, one might expect to have problems of bonding with this type of arrangement. This same type of effect is much more noticeable with higher currents, and so we've done similar experiments with currents factor order of magnitude higher, and again, cell calibration appears fairly linear. Gas production deviates a little bit, but not greatly in linearity. And again, the time history is shown here. We're now, with this type of arrangement, getting up to fairly high temperatures, 9 degrees or so, equilibrium after about 400 minutes of a typical run. These two curves shown here are for power inputs of around 7 watts. Again, if I overlay the result with thin foils, there is a similar effect observed. Deviation begins someplace around 200 minutes. The deviation is much magnified with the higher currents and higher temperature. Hard to tell which is most important in this. Deviations being orders of a watt, which again, if you consider the small volume of the foils, represents orders of tens of kilowatts per cubic centimeter in foil prior to its self-destruction. So, in summary, Our swimming electron layer theory predicts that there will be very high reaction rates at the interfaces of thin films and materials having a large Fermi energy level difference. Our predictions, as a matter of fact, were, if you look back in the last meeting's paper, theoretically we calculated about a kilowatt per cubic centimeter, so these results I'm showing are not unexpected from that point of view. The technique for developing these thin film electrodes has been developed and is fairly routine now, but still tricky to get decent surfaces to avoid excessive diffusion of the two materials together so you have a distinct interface and things of that nature. The experimental results that I've shown I would not class as anything but very preliminary, but they are suggestive of very high power densities in these thin films. Incidentally, all 5 experiments to date show behavior something of the type I showed you. They seem to be reproducible in that sense, at least prior to disintegration of the films. The failure of the films terminated the experiments in all cases. The higher currents, the termination usually occurs a little bit earlier, after about 400 minutes of operation. We've gotten up to 700 minutes of one of the low current runs. Exactly what's causing the failure, one's tempted to jump to the conclusion it's due to the internal heating, but it might be other types of effects that we need to investigate. We're examining these very carefully with electron microscopes and other metallurgical techniques. At the moment, our conclusion has been that our main problem is bonding between the multiple layers and the substrate, as opposed to bonding between the individual layers, i.e. it looks like the flaking has occurred between the substrate and the layers rather than between individual layers, which is encouraging because we think that there are ways of getting better bonding to the substrate and change that. So we are hopeful that with that improvement, this could be potentially an encouraging route to heat production by these methods. Thank you.
Of course, you have a differential extension here. You're charging the inner palladium layer, say, through the palladium-titanium structure.
Yes.
And you don't have much of a diffusion. You have a big difference in diffusion coefficients too. Right. So you'll have a problem, and you might really do rather better by using a single film. And there was a lot of work of producing films of these types of materials on wire, beryllium copper, in the wire memory time. You might like to look at what was produced in wire memories, because these were produced electrochemically and had to produce stable structures as well, with good adhesion.
Sounds like a good suggestion.
That's
a good suggestion.
Yeah. And the other point, of course, is that you might do better. Palladium silver is a good material for evaporation, because electron microscopy tells us that. And of course, in this integrated circuit area, you usually use tantalum as number layer. Or that will hydride also. If you don't mind working with beryllium, then beryllium copper would possibly be sensible substrate, if you can get hold of some old wire from the computer memory.
All very good suggestions. The bending of the films reminds me of pictures that Yamagachi has shown of his experiments. Show this bending.
You mentioned 2 different calibration curves, one at low and one at high temperatures. I'm confused about that as to which one you actually use to analyze your data. And secondly, you say you have a twin calorimeter, at least that's what it looked like in the design, and yet you get absolute temperatures on your curves. What feature of the twin calorimeter do you actually use?
Well, let's say the first explanation. The first is we've done experiments both at low currents or low power inputs and at high power inputs, and so we have different calibrations for the two different cases, and those were shown. So we're using both. The dual cells are probably redundant in a way, but what I showed you was the time history in the twin cell as the experiments proceeding versus that in the multi-layer cell. So they were done simultaneously.
Did you make any experiment with various thickness of the materials so that to be able to refer to the RCC of particle?
We plan to do that. Thus far, though, we produced all 5 of these electrodes simultaneously because we can actually, in the vacuum vessel, put 5 targets in and do the coating all at once. We have additional ones that were made that have various materials and various thicknesses, and all it takes now is time to look into that, and there's some good suggestions such as Dr. Flashman just made, and others when we go home will even make some more.
Why did you choose to run the 2 cells in parallel? You could have done it in series, obviously. You must have done it for a reason. What was the reason?
Well, we felt that this was the best way to control the power constants in the tube. But we could run it in series also.
The choice of this title came from discussing what I was going to talk about with my wife. It was a movie buff. And she said, what you've done is you've taken advantage of hindsight. And I want you all to know that what I'm going to tell you could possibly have been known in 1989. I am an amateur archaeologist in the history of science, I guess, with the assistance of my colleague, Wilfred Hansen, and we've had a good deal of cooperation from some of the early players. We've had a luxury of time, which those who started this series of investigations did not have. We've also had the benefit of all the mistakes that those who have done experiments did not have during '89. And so if you wish to understand what the title of the talk means, it means if I had it to do over again, given what we actually knew in 1989, how would I kind of think it ought to go? I've read a good many of the books. I've talked to a good many of the people. And if there's one thing that I guess we're all well aware of, is that there's an awful lot of noise in this system. And it comes from different regions, or comes for different reasons at different times, and things kind of get very excited very quickly whenever you talk about this subject. So with that, let me structure what I'm going to say to you around what I think are probably the two communities of interest which seem to persistently ask the question, is the Fleischmann-Pons effect valid? The communities of interest, and they're not independent, the scientific communities and the technological communities is represented by the Patent Office and the interactions that it imposes upon those who wish to take advantage of the possibilities that were proposed by many people in the press during the early days of this subject. The scientific community has a continuing discussion with itself as to what business it's in and what constitutes validity. And I've participated over the years in a number of scientific review panels. And review panels for various purposes. Those of us who sort of reach my age end up participating in review panels which are associated with the distribution of money. And the distribution of money, except in a time when the economy is expanding rapidly, tends to be a zero-sum game. And so when a panel is impaneled, there's always the problem of how one chooses members of the panel and what charge you give to that panel. I will not dwell too long on the Patent Office side of it, but I do want to say something about the Patent Office and its criteria. And in particular, there are three criteria, not totally mutually exclusive, which the Patent Office insists upon. Newness, which means that you can't go out and buy it. It's somehow new. Now, new is a very difficult term to describe, but newness has been in the evolution of patent law in the United States for a very long time, and it's had an up and down career. It got to the place where the courts would change the definition of newness about every 30 years, starting about 1820. Usefulness is the place where a juncture comes between the scientific community and the technological community. Useful means operable in some sense. That also fluctuates in definition. And it also means then that it can't be a perpetual motion machine. It's the place where scientific validity has an intersection with the Patent Office's criteria. Non-obvious is a creature of the law in the 1950s. In the 1950s, one of the Supreme Court justices writing on a patent case essentially laid down a criteria for newness, which said, if you're going to invent something and claim the rights of patents, what you must do is get a Nobel Prize. This was considered generally a distressing development in the patent community, and Congress changed the law shortly thereafter. And non-obviousness caused the creation of a mythical legal term, or a legal person, called the person who has skill in the art. I haven't got it quite right, but at any rate, Phoebos or something like that. And what it means is that if you're informed, if you know how to practice the art, and it was not clear to you that this thing that's been presented as a patentable item shows up, then it can be said that the person applying does have a right to get a patent on it. Needless to say, this is also a playground for the legal community. In a truly news field, of course, knowing who's skilled in the art gets to be a rather interesting thing. Now, the Patent Office is a bureaucratic organization. It's not in the business of ratifying anything, but they're very proud to report their activity. And I think it's interesting to read what the Commissioner of Patents has told us that he did in fiscal year 92. This is an interesting statement for several reasons. One of them, it says that people believed that they had discovered something and that they were willing to make the effort and spend the money to lay claim. So there were 200 applications mentioning cold fusion as of the end of 1992. And it's curious how that mention can cause you to fall into the category of being a cold fusion patent. There was a patent which mentioned fusion, loading of palladium with deuterium, which was issued this year. It did mention fusion, but it didn't mention cold fusion. It did, however, reference an article or a publication, a research publication by Professor Fleischmann of 1972 as the starting point for their work. So it was filed a week after the announcement in March of '89, and it was granted this year. It's interesting, the examiner who's handling these 200 patents is not the examiner who handled that patent. So within the Patent Office, what falls into the category of the 200 and what doesn't is a bit arbitrary. The last point I wanted to make, and then I'll get off the Patent Office, is that these applications have been routinely rejected under 35 United States Code 101 and or parts of United States Code 112. I can paraphrase what the rejections consist of, what the routine is. The routine is as follows. On the basis of high-quality research results presented in the scientific literature, and then they proceed to list them. The Journal of Electroanalytical Chemistry, the Wall Street Journal, the Washington Post, the New York Times, Fusion Technology, and a similar collection of that sort, and internal reports of various government agency trips. What they have succeeded in doing is establishing beyond a shadow of doubt that this claim for cold fusion falls in the category of not useful, on the basis that it is not operable. In other words, it does not accord with the laws of physics. Oh, by the way, among the references and these sorts of things are the product of review groups. Review groups such as Secretary Watkins formed in the early days of this subject. I'll have more to say about that. But at any rate, so the Patent Office rejects you on that grounds. Now, the next part of the Patent Office requires you to be a lawyer to really appreciate. What the next part of the Patent Office's rejection consists of is you can't possibly get a patent because it's not new. And the reason it's not new is because there's this prior art, which has already been patented. So the legal situation in the Patent Office at the moment is that, first, the phenomenon does not exist on the basis of the profound wisdom expressed in the literature and understood thoroughly by the patent examiner who is building the case. And if it should turn out to exist, you can't have a patent because it's already been discovered and a patent. And that is the legal situation. And therefore, let me depart from that side of the house because I'm not a lawyer, although I grew up around lawyers. I'm not a lawyer. My father's a lawyer. He tells me this makes sense. I'm sorry. What I would like to do is I'd like to restrict my commentary to the the top part. And I want to go back, and I want to talk about the papers, the scientific papers, which I think are the foundation for a good deal of what we understood in 1989. Now, I've been very selective. I'm not much of a Democrat, small d. I'm much more inclined to kind of follow my nose in terms of people who seem to make diligent efforts and have a chance with the resources to do some good experiments. And as I read the report of the Energy Advisory Board, they did very much the same. The advantage I have over the Energy Research Advisory Board is that I have 2.5, 3 years of looking after the fact at what was available at that time. It also turns out that what was available to them at that time wasn't really complete, nor understood, nor was it all available. So let me start off by generating a little bit of a chronology here of experiments and their reports. And I will make a point that from March until this field was put to bed, as far as the official community was concerned, was sort of the 1st of April, the end of March, until the 8th of November, which is quite a short time. In fact, it's so incredibly short, I'm amazed in retrospect at the incredible energy that was devoted by an awful lot of people to try and get as much out as they did get out. And also, I've tried to ride one of these review committee reading sessions and trying to get 25 or 30 people on a review panel to produce a coherent document. It is a prodigious task, and it assumes, in the first instance, that the notion of something being well described means that the choice of descriptive terminology and language is in reasonable consonance with the expertise of the members of the panels. If you're in a truly new area, it may or may not be the case that experts can read efficiently, so they have to study. Those of us who learn the computer programs know that there's always a trade between learning to get the computer program to work and getting the job done, particularly if the manual is quite thick. There's a similar problem here. I did a count on the number of references that were listed in the ERAB report, the Energy Research Advisory Council report, and there are 114 listed. There's some 30 members of the committee. They were on the road. They didn't have this just as their only job, and so they had a problem. So now let me be critical for a moment of some of the papers. The very first paper was published on the 10th of April, and the thing that you get out of it is that we don't know when the experiments started. We know they were finished because there was a submission of this paper in about the 12th of March, and we have very little information on the performance of the system. The next thing we have is we have a series of efforts by Lewis and Company at Caltech, which was published in Nature in August. Their paper was submitted on the 22nd of May. We know they started in early April. We know they ended in early May. They claimed 0, and they said that they had about a 6% accurate estimate as a function of PD input. We have Williams' work, which started in mid-March and ended in late July. Their paper was submitted for publication in August. There were various uncertainties. They said they got no heat. And one of the other interesting things is that Lewis and Company, the maximum length of any experiment they did was 18 days, excuse me. I've talked to Professor Lewis, Group and I went down and visited with him, and he basically said that if you really want to do anything decent in looking historically at this stuff, you really ought to go to Williams and Company at Harwell. What we have done, what we have been fortunate enough to do is we've been fortunate to get the cooperation of the Harwell organization. We have all the data, we have all the logs, we have all the people. And let me just turn the slide projector on back there a minute. And this is about the size of the team that was doing the calorimetry. This is David Williams. This is David Williams on the right. This is Derek Craftsman here, who did most of the calorimetry work. And the other two gentlemen I never have met, but I'm told that they were involved experiments, and that's about the size of the crew. Next slide, please. This is Derek. The apparatus that you see consists of a computer system which was put together to collect the data on the fly. I mean, this thing got put together very quickly. This is the box which is filled with the calorimeters. These are neutron counters above. This is the instrumentation for powering the calorimeters. Next slide, please. This is Derek with the neutron counters lifted off of the cells. Next one. And these are the cells. And what you have here is you've got a row of 4 cells with 6 millimeter diameter rods of palladium. These two have lithium deuteride, lithium hydroxide, sodium deuteride, sodium hydroxide, 1, 2, 3, 4. And then what you've got going here are 6, 4, 2, and 1 millimeter electrodes. This was a matrix experiment. Current ran through these things in series. And I guess the point I would make is that they attempted to do a lot of the things which people complained about. Next slide, please. What they found is they could not analyze their data, so they set off to build alternatives. Next slide, please. And they couldn't get those to work, and so what they did is they got themselves a plutonium calorimeter, which is the world-famous, highly accurate, precise calorimeter. The only problem with it is it too had problems, which when you look at the data, it turns out that they didn't have any blanks for this one. It was betting that this thing was always going to work properly every time. And you can see Derek over here collecting data by hand. Next slide, please. And then over here, what he's doing, he's annotating the log. We have these logs, and the point I guess I would make is that when you get all done, what you find is that they tried very hard. Their entire set of work took 3 months, and they all to a man say, we would have never published our paper because we did not understand our instruments. These people at the top were all in the glare of public scrutiny. There were other experiments going on. At the bottom. Is one in particular that I've had made available to me within the last year. And I guess the thing that I should point out is that these people had an opportunity to build an experiment, find out what was wrong with it, build another version of it, find out what was wrong with it, build another version of it, and actually make it work. You can see the accuracy over here. The result of all of this is that this experiment represents the kind of thing which in the public literature was not going to be achieved for some period of time. That was not available to ERAD. I'll wrap up by simply pointing out that understanding the experimental apparatus was not a luxury that the Harwell people had, and that the argument that they made, and my colleague Will Hansen will talk a bit more about this, is that critical to all of this is an estimate of the control limits. The control limits, as established in this experiment, were the 2 sigma limits, where sigma was defined in terms of a 5 to 10% error, which is associated with the measurements made. They did sort of differentiate these 2 classes, deuterated and non-deuterated cells, and ask whether or not there's an energy difference. If you follow the Harwell prescription, and you do the analysis on their data more thoroughly than they had available time to do, what you would find out is that using their arguments, their cells would meet their criteria of having observed an excess heat. Using their argument, but just processing their data more effectively, taking available data that they had. I want to conclude, if the chairman will allow me, with a number of observations. First, you can indeed take advantage of 300,000 pounds spent by another experimental team to good effect. Second, these are not complex instruments in the usual sense, where complex is a count of the number of parts and their interactions. These are subtle instruments, as we have been seeing for the last couple of years. And that subtlety tends to get lost in the kind of cacophony which occurred in 1989. Crash project experimentation does not lead to an understanding of subtle points in instrumentation, which are the foundation of what you're doing. Most, not all, most 1989 experiments were done too hurriedly. They didn't really know where they were going. Folks at Harwell thought they were replicating the work, and yet their designs are radically different in important ways than those things that they thought they were replicating. If you're too visible, you have too much company at the front gate. And the result is you do not generate reliable scientific fact. Exaggeration was the name of the game in 1989. That doesn't lead to very cool heads operating. It is very difficult if you're on a review panel with 114 references, 6 laboratories to build, and an awful lot of rather strong personalities to reach any conclusions which really are robust. I must say, after having read the report of the Energy Research Advisory Board, it is as carefully a crafted bureaucratic document as I could have written. However, there is insufficient evidence in what they were doing to draw the conclusions which people claimed the report produced. And the last point I want to make is that at this juncture, I think it's fair to say that the Fleischmann-Pons effect exists. Heat is its signature, and I'm following on Mike Kruger's observation about there are 2 hypotheses, and the first one has to do with heat. Mature experiments produce facts, not beliefs. Fritz Will this morning pointed out what it takes to find tritium. And last, explanations come after you have good experiments. And I would only make one last point, Fritz. The Amoco people did see tritium at a level 2 to 3 times higher with really good instrumentation. Thank you very much.
Thank you. Can take just a couple of questions to start with the Fleischmann.
Who was the third group that replicated the experiment after Williams?
Amoco, their laboratory in Oklahoma.
Before you disappear, may I ask you to put your slide of Lewis back up? Because I have a particular graph about that. The point, you are being generous. No, the one on the table.
Oh, on the table.
Sorry. The point is that you say you started work in April 1989 and finished in May 1989. Now that is true, but of course up to the time of the meeting of the Electrochemical Society in Los Angeles, which was I believe on the 17th of April 1989, Lewis used the incorrect calorimeter design. So either his experiments, which he reported, were not taken in the calorimeter as he described, or he did all this work between the 17th of April and early May.
I will point out that the official chronology of the evolution of the experiments at Caltech are contained in Engineering and Science, the alumni magazine of Caltech.
Well, that's always incorrect. It should be corrected by
it is scant on those details.
The other point, if I may just make the point, is that I have been struggling with trying, or Stan and I have been struggling to understand the Harwell version of our instrument. And I think we've so far spent 18 months on that, and we are not at the end of the road.
We've spent more time processing the data than Harwell did. I mean, Wilf and I, and I've hired several people to work on this.
Okay, really not short of time, but can you have a quick question, Gene, and very quick.
Try to be real quick. I noticed in the chart we do not have MIT, Plasma Fusion Center report. I just want to say that I have some familiarity with this as Dr. Mitchell Schwartz of MIT. I just want to summarize briefly. In May of '89, the Plasma Fusion Center team, chemistry department team, came to the conclusion that Pons and Fleischmann's experiments were all wrong. And on June 26th, they held a wake for cold fusion at the Plasma Fusion Center. What's interesting about this is that wake was held prior to reducing their data. Their data was not reduced until July 10th, '89, and there was a subsequent change in that data on July 13th of '89, which is the subject of a Fusion Facts article authored by Dr. Schwartz. I would advise anyone interested in the history of cold fusion to study the what can only be described as a significant manipulation of that data to a zero result when in fact they probably have excess heat.
Can I just comment on, on Gene's? I realize, as I told you, I've been very selective because I've been able to get my hands on the data, or I've had direct contact with the experimenters in everything I've talked about, and I've been in the laboratories. I've chosen those sets of things which, from spending the effort, one's able to get some sense of what was going on. A one-day visit to a laboratory, I find generally inadequate. I've been to Harwell now for approximately 10 days visitation and working in their library. I've spent a lot of time with their people. I hired a fellow who did the data processing to work with me for about 8 months. So the effort it takes to do archaeology is non-trivial, and I know Mitchell has done the same thing. But since I do not know that personally, I'm not here to do what a lot of the people who have talked about and commented on this subject have done, and that is read abstracts and listen to what's on the jungle drawings. So I'm attempting to get back to my construction of the future. Back to the future number 4 to me is basically we managed after 4 years to get to the place we can do science again on a subject which is not determined by what the explanation for the heat is, but the heat is the primary thing.
My only main point on that was, just to close, is there is no question, I think, by both the opponents and the proponents of cold fusion, that MIT, Caltech, and Harwell were the key negatives that drove the media and government policy on this subject. Those 3 need to be considered as the prime drivers. And I wanted to add that. Thank you.
Thank you for this. I think we should move on at this point. I apologize to the other people who want to. We will have time after Dr. Hanson's talk, which is similar. So please, Dr. Hanson, if you talk. Well, I'll let you get right.
No, I don't have it. Go ahead and read it.
Okay. It says palladium heating calorimetry, the key to the Fleischmann-Pons effect and a challenge to science.
Thank you. I don't know about this. I'm a professor and I don't give 20-minute lectures. But I'll sure try to cram it in here. Excess heat is the signature of the Pons-Fleischmann effect. We all have to agree with that. To get right to the point, if that excess heat comes from nuclear effects, then there must be some special means of transferring the energy of the highly energetic particles to the labs, because it doesn't show up. And as a matter of fact, if you look at it as a quenching, then what high energy stuff you do see is just left over and probably very fickle, because the main reaction is going somewhere else. Now, that is such an affront to nuclear physics as we know it, that is an enormous challenge. And it brings up the point, I would like to say, what the main purpose of our meeting here is. I practiced in the other room, so I'd be sure to know how to do everything. Then they told me this was the room. By large amounts of heat, we mean heat so large that it's impossible to explain it in terms of chemistry or metallurgy. The only way to measure that kind of heat is by calorimetry. And there is perhaps one exception to that, and that might be these days the measuring of helium-4. But to date, really, the only way to really examine the Pons-Fleischmann effect is through calorimetry. That brings up the next question. Is there really any data which definitely says that this is true. Well, now, if we take seriously many of the papers we've already heard at this conference, let alone anywhere else, the answer to that question is a resounding yes. But the implications of that are so fantastic that you really can't blame scientists for being very skeptical and very cautious. And besides that, there's all kinds of loose ends that aren't cleared up yet. I dare say, with a smile on my face, because I might be one of them, or even a few people on your side sometimes who wish on the other side.
I do.
Anyway, there's a lot of loose ends. There's even some loose experiments. There's all sorts of things. And believe me, there's room for all sorts of thinking on the subject. But, and if I can go on with the thoughts that I've tried to cram down here, how do we really decide when it's being proved? That's kind of a matter of opinion, isn't it? Has it already been proven? Or when will it be proven? Well, I think we have to think about what constitutes proof. And by no means am I going to sit here and give you a lecture on what constitutes proof. But I would like to put in a couple of words. One is, I'll tell you how I would not prove it. And that's by counting pluses and minuses. It's perfectly natural that most of the experiments in this unknown area are going to fail. That's just the nature of science. Taking some kind of a head count on this, to me, seems very meaningless. But on the other hand, so does something else, and yet we're kind of in a dilemma. What a waste of time it is to have beautiful equipment, especially if you're well-heeled and well-funded, and spend time and money making measurements on a dead cell. No, I mean, you didn't see this, you didn't see that, you had upper bounds on this and upper bounds on that. Well, really now, if the cell isn't working in the first place, you're not going to see much, are you? That seems to be the situation here. The real trick is to figure out when you've got a cell that's working and then augment your experimentation. Well, if you don't even know what working means, that's kind of hard. But I think maybe we're getting closer to knowing what working means. Well, a lot of things have changed. I believe we know a lot more about how to find out the answer to that question than we used to. I think when I say something ambitious like that second question I put up there, I don't in any way mean to pretend that I can answer it better than any of you, but taking a very small subset of this whole thing, I will suggest a few things and maybe give you some interesting data. Some data are not as dead as you might think they are. For example, tar well data. Now this is put up more from the standpoint of how we looked at it, and I'll only be able to spend just a few things on that, a few minutes on that even. Here's an example of the drawing of the calorimeter by the authors themselves. There is a thing about this that's kind of interesting. One of the things that turned out to be a bad feature, but was put on there for a good reason. That line that goes up like that is actually a heavy glass hood or bonnet, and the electrolyte is up to here, the bath, I mean, is up to here. And so this particular thing is a very good conductor. The electrolyte's right up to here. So you've got a nice path right up to there. Not only that, you have this tidal effect in which this thing goes up and down, the level of the electrolyte goes up and down every day. And so you get a great big change in the conductive part of the heat transfer coefficient. And that is a problem. Nevertheless, it had some good features and so forth. So I can't really say much about it. There it is. Now let's give you an example of after our treatment of the data and some of the results coming out. I'm not going to have any great big surprises here, I don't think. So don't expect me to suddenly should the answer to everything here. This is the excess heat plotted as a function of time. But the excess heat is not only there, but in this particular graph, the heat pulses were put in there, and they put many and varied heat pulses in there. They also changed the current all over the place, which is not in there, and the fact that it doesn't show up is good. It's been calculated out. But anyway, the first time up to about here, many things went on. They hadn't really settled down as to how they're going to do the experiment. And so I suppose there's good reasons why this can't be analyzed. Maybe on closer look we can get something out of it. Now this particular thing is designed to give us 0 if there's no excess heat at the beginning of each daily cycle, or whenever it was the cell was topped up, which was not every day, it was only in certain times here. But anyway, so it should, if we're right on 0 there, that would mean that there's no excess heat. Well, to make a long story short, across this whole region and in the heat pulses and so forth, this comes out to be about, you can come up with an error of about 20 milliwatts for this whole thing. And that, of course, is enormously better than they claimed to understand their cells. Now, since I don't have time for a lot of things, let me just say that that whole matrix of cells that Mike showed you, and now I'm speaking for myself, I will say there's only one, but I would say showed excess heat. But it definitely showed some excess heat. And the rest of them, within the areas I'm talking about, in the regions that were analyzable, which is most of the region, essentially, just like Harwell said, got 0 excess heat. But again, I say, that's no great big surprise. Now let's take some of, now I have to be really careful because the authors are present. Here's a Pons Fleischmann cell, and the particular data that I have came from this kind of a cell. I can't get the whole thing on there, but I'll use dynamic scanning here. This is the cell, and notice that it's deliberately silvered in this region so that when it went up and down during a daily cycle, it would not change the conductive heat capacity, heat transfer coefficient so much. And the conductive part is only a small part of the whole heat transfer coefficient anyway. Most of the transfer is radiative and goes to Steve IV and is through the Dewar part down here, which is an unsilvered part of the Dewar. Now, I'll present a cell that is difficult to analyze. For one thing, it doesn't have any heat pulses in it. So how do you calibrate it and so forth? Well, it turns out that it works out very nicely. Have programs that give you, that will analyze the whole set at once and give you a Q, a K, the excess heat, the heat transfer coefficient, and the heat capacity. Solve them simultaneously. And then, using the Q and the M, solve point by point for the heat transfer coefficient. And now, this is the conductive part, and Mark will complain because I made it too big. Now, that's somewhat arbitrary. I believe it's bigger than he thinks it is, but nevertheless, it's not as big as it is shown here, quite. But it turns out that this goes changes shape depending upon what you give it. You see, I've distributed the heat transfer between the radiative and the conductive, and I've done that somewhat arbitrarily, but not completely so. Okay, but this is a real set of data in the sense of its variation, and even if you make it smaller, it will still have, the variation is thrown into the KC, and as a matter of fact, each day you see as the level goes down, you get this change, and then it's topped up. And obviously there's some things that are not exactly the same in here, but there's a few remarkable things about that. One is that the temperature there is about 91 degrees centigrade, where we finally quit using the data. By the way, the rest of the data aren't used. But that's much higher than the 60 degrees people used to quote as the very maximum for this type of calorimetry. But I want to now show you that now I go back and calculate the excess heat. And here we're talking about calorimetry, not finding excess heat so much. We're trying to show you what we can do with this. Here's QF, and the QF for the situation I just gave you is this top curve, and it goes over and is like so. And once again, if you take the sigma is about 10 milliwatts. The way I look at it, it's much less than that if you actually take the random error sigma. But I've done it taking various sections and various ways and use the sigma, estimate the sigma, which includes systematic error. Now, just what made this difference here? I just want to show you something. That's using 1 atmospheric pressure. This is using the atmospheric pressure expected at the time the experiment was made in Salt Lake City, Utah. So you do have to take into account all kinds of little details. Now, there's lots of other things we find out about this calorimetry. I'll just give you a little flavor for some of the things we did. One of the things people have proposed is that all these cells, after all their glass, are sitting there talking to each other. They radiate toward each other, they exchange, and with the background and so forth too. I made a systematic study of that with regard to these are black body radiation curves, and notice where any significant amount of area under that curve would be. And surely you could go out to about 4 microns with almost nothing. You see the point? Somebody have a question on what I'm presenting right here now, because I want to do it quickly.
Where's infrared on there? Can you point out infrared and ultraviolet? Or
I can't even hear you.
Infrared, ultraviolet, where's the...
0.8 microns.
4 microns is right there. And you got to think about that whole curve and what fraction of the total radiation would be involved in something that was transparent only to the left of that.
Ah, okay.
See, that's the point. All right, now, I personally measured the transmittance curves for light water, heavy water, and Pyrex. And this happens to be light water and heavy water, and notice that even if it's a couple of millimeters thick, it's dead. You're not going to get any of this appreciable amount of radiation through it. And that's not quite so true with the glass, but it's approaching similarly. This also means that when I show you the next picture, which is now up at, I went up there to 600 degrees Kelvin, because people have suggested maybe you can take a video camera and see spots in the electrode where you might have hot spots and see where things are happening, and that might be a great idea. Unfortunately, you're never going to see it, because even at 600, you see it's all absorbed by the water, by the bath, by the glass. You're never going to see it at all. But that's the bad part. The good part is that it's also no problem. Well, there are other things. Temperature uniformities. We actually have some of these cells, and we're playing with them, and so forth. I would just like to say, in closing, that open calorimetric cells are useful and are still being used. And I would also like to say that with our advanced techniques in analysis, which I've only been able to say just a little bit about, the old Pons-Fleischmann data still shows excess heat. Thank you.
I want to compliment Dr. Mellon for his original, the first paper that I'm referring to, for his analysis. I also want to put a little bit of hope on the part of people who have been fighting the patent office and say a little bit about that patent. Dr. Fleischmann, this is partially for you. The Do4 paper that was given just before the lunch stressed only the theory. The experimental part is in fusion technology. And I would advise everyone here to read it. But in addition to that, there's a very important patent application that Shell took out for the European community patent for a patent from the European Community Patent Office. That patent is very cleverly written by very competent big corporation lawyers, and I stem from the same sort of research community and competitor of Shell. There isn't a word in that patent about cold fusion. It is about the production of energy. And I venture to predict that it will have a chance of being issued. And if it is once issued, I venture to predict also that a combination of the issuance of that patent and the current economic crisis where the classical physicists are hard put, they may be flocking into cold fusion as a way to maintain an economic existence. That's all.
Can I make a comment on that? They might do it for the sake of the field, but I'm sure they wouldn't do it for economics.
He is professor at the
clinical somatolysis. I work with him for almost 20 years now. Today, I want to talk about the heat measurement. Since Professor Rishman, Professor Hans made an announcement about cold fusion, there are two groups this research. One is Professor An Xu Wu. He got with his college got the negative result. Almost at the same time, we got the positive result. Our institute believe them. They doesn't believe us. Why? Because they use the calorimeter almost the same to the instrument Professor Friedman and Professor Hans used. We used the calorimeter. It's a commercial calorimeter. It's a micro calorimeter. It's one type of carbon type of calorimeter. This kind of calorimeter is different from the what calorimeter used by most of scientists here use. This is a calorimeter vessel. Is a cylinder inside. This is a bigger aluminum block. Between the two walls, there are so many carbon, some bell connect them. We measure the heat. Notice in energy, in power. Why? Because some carbon measures the difference of temperature between the inside and outside in the system or surrounding. The heat should be conducted from inside to outside, or from outside to inside. If the heat generated inside, the heat should be from inside connected to outside. The heat in power will be measured by the voltage because it's some carbon. We don't need to measure the temperature here. As you know, our experiment is the electrolyzed process. Should we measure the solar power with the phenomenon? If we measure heat in energy, we should be
should be charged still, and how long you charge this still, and then you can measure the heat in energy. But in our instrument, we just measure the voltage equals to measure the power. We use the equalized cell. It's like this. This is a cathode in the center of the cylinder. Here is a glass vessel. This palladium is a cathode. This is palladium mixed with air. Around the telephone tubing. You can see here, if the oxygen produced outside of this telephone tubing should go out from here. And the hydrogen or different gas generated from here should be escaped from this way. Not that is to be a mixture. Avoid the heat from reaction oxidation of the neutron of hydrogen. We measure we put this the cell into the calorimeter. Here. And we use the constant current power supply for this experiment. We just monitor the cell voltage. We can monitor the power in. At the same time, we measure the voltage from the solar couple. We can measure the heat generated in the calorimetric system here. Before we measure the thermal power generated in our system, we should check the electrical system is ideal cell or not. As I told you, we can monitor the cell voltage. At the same time, we can measure the current for the electrolysis. You can see if we use the current is less than 1 milliampere, we got the relationship and got for the high water almost close the 1.54 or 3. if we use the night water, it's good source. And then we should calculate our calorimetry. We using the about 10 milliwatt. At the same electrical power, we got the constant of the operations. The average is this one, and the precision is about 0.4%. As you know, our system not exactly at the same power charge the electromagnetic cell. We had a calibration of our calorimeter with less than 10 milliwatt. You can see there are good relationship between the wattage and the heat metric. And we worry about is too small. We should large. In a bigger than that. You can see there are good relationship between the what is electrical power supply. And another thing we needed to do is that calorimeter curve should be correctly. Why? Because we always record the curve should be destroyed by the instrument. You can see this curve is show the record. Actually, we put the heat into our system. It's like a square. We record the curve. It's like this. Much different between them. We should have a reconstruction with the curve. We're using the two function correctly. Sorry. We're using this correlation because this data shown here. This is the current function.